In this example, we're looking to find the equation of the line tangent to the graph of f of x equals square root of x plus 2 at the point a equals 7, which is an x value. And we'll be using the limit definition of the derivative here. So when we're asked to find the equation of a tangent line, we need to remember simply what the equation of a line looks like. So let's bring up the point-slope version of an equation of a line. The point-slope form of a line is one of the most useful equations from algebra now that we're doing calculus, and it's given by y minus y1 equals m times the quantity x minus x1. And recall that x1, y1 is a point, so these are going to be a coordinate, we'll say, okay, and x and y are variables. So we need to figure out what x1, y1 is as a point. Well, we're given the x value, so we'll call this a is actually x1 is 7. So then to get the y1, we just take f of x1. Well, that's f of 7, which is the square root of 7 plus 2, which is square root of 9, which is 3. Okay, so our point that we're looking at finding the tangent line at is 7, 3. So that's our x1, y1. Okay, so we got that down. And then in this equation for the point-slope form of a line, we'll leave y and x as variables, so those are okay. The big thing we need then is m, the slope of the line. Well, remember that the slope of a line at a point is given by the derivative of the function at that point. So the slope is going to be f prime of the function evaluated at x1, which is 7, so f prime of 7. Alright, so let's first find f prime of x, and to do that we need our limit definition of the derivative. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. So let's dive in. We have the limit, alright, as h goes to 0, f of x plus h is square root of x plus h plus 2. I'm just replacing x with the quantity x plus h. Minus, okay, now we have f of x again. Whoops. X plus 2 is just our f of x all over h. So there we have our f of x plus h and our f of x. Now our goal is to get rid of that h in the denominator, so we're not forcing ourselves to divide by 0. There's a trick to this. It is going to be multiplying by the conjugate of those radicals there. We call that the conjugate is just changing the sign. I guess it's easier if I just show what it is in this specific case. But it's super useful when we're dealing with radicals in situations like this. So I'm going to say the same radical, x plus h plus 2. Now instead of a minus being between them, I'm doing a plus. That's the conjugate. Plus rad x plus 2. Okay, over. Now we want to multiply by 1, so we have to do the exact same thing in the denominator. X plus h plus 2 plus the square root of x plus 2. Alright, so really we're just multiplying by 1 there. That is the conjugate trick. Super useful. So when we FOIL that numerator together, look what we get. So we get the limit as h goes to 0. We get x plus h plus 2 minus the quantity x plus 2. Look at that. All over, and then the denominator becomes quite the disaster. Square h times the square root of x plus h plus 2 plus the square root of x plus 2. Oops, okay. Now up in the numerator we have some nice cancellation. The x's cancel and the 2's cancel. And what that leaves us with in the numerator is simply this h, but we have another h down here in the denominator. So now those will cancel as well. And now we have something we can work with because we got rid of that h in the denominator, which was the entire goal. So we have the limit as h goes to 0 of what's left. Well, just a 1 is left in the numerator. Down below we have x plus h plus 2 plus, sorry, that's the square root of x plus h plus 2 plus the square root of x plus 2. And now we can let h go to 0. We simply plug in 0 over h because it's continuous at that point. And we get our final derivative of 1 over 2 rad x plus 2. Okay, so that function gives us the derivative anywhere We, in particular, want the derivative at a single point, x equals 7. So f prime of 7, now we can figure out what the slope of the tangent line is at that point. So 2 rad 7 plus 2, I'm just plugging in. Well, that's 1 over 2 rad 9. Okay, so 1 over 6. And this is the slope that we've been looking for. So going back up to our line here, okay, so we can plug this into point slope form. We have y minus y1, which is 3, equals m, the slope, 1/6, x minus x1. We decided x1 was 7, x minus 7. Okay, when you're giving the answer and it's a line, you don't want to leave it in this form. You want to put it into slope-intercept form for your final answer. It just looks a lot nicer. Slope-intercept form is y equals mx plus b. Okay, so it's just a relatively straightforward algebraic manipulation from here. Let's see, y equals, I'm just going to distribute this 1/6 through and add that 3 to both sides. So 1/6 x minus 7/6 plus 3. Let's grab a common denominator here to take care of that 3. We'll go 6 over 6. So that gives us y equals 1/6 x minus 7/6 plus 18/6, which gives us a final answer of y equals 1/6 x plus 11/6. There is the equation of the line tangent to that graph at the point x equals 7. Let's just check this out in Desmos real quick here. We have our function, the square root of x plus 2, and then we have our line. So what did we decide that was? Y equals 1/6 x plus 11/6. And there you can see the function. Let's zoom in right at the point x equals 7, so that would be here. What am I doing here? Let's do this. We do 7, 3. There we go. Really put a point on it. No pun intended. And here we have that exact point. So the red one is our square root function. Our bluish purple looking thing is the tangent line, and you can see it just touches, the tangent line touches the function at that one point and then goes off. Right? So zoom out and zoom in. You can see it just barely touches the function at a single point, and that's all we need to find the line tangent to the function at a single point.